Have you ever heard of self-destructing malware? What I mean by self-destructing is that the malicious executable or the malware erases a crucial part of its structure to avoid being detected and dumped from memory at runtime. Before we get to the code, you should know that the portable executable file structure consists of two crucial segments, headers and sections. The sections contain the executable code, variables, relocations, etc. The headers, on the other hand, contain what you can call the identity of the portable executable. Without the headers, you can't even tell the file type that you're dealing with, which makes it more challenging for AV solutions to detect. So here's the plan. We will create a kill switch inside our malware that erases the executable headers if it gets detected. I picked this technique specifically because it demonstrates how we can manipulate a portable executable structure. So I believe this is one of the most important videos in this malware development series so far. So stick around, I'll explain everything from A to Z. Anyways, let's look at the code. Here in the main function, we call the self-destruct function. The code in this function is very simple. But before we dive into it, I just want to clarify something. What I mean by the portable executable headers is all the bytes starting from MZ all the way till the first byte of the code section, because this is where the first section in the executable starts. What we want to do is to erase or delete all of these bytes, starting from MZ all the way to the code section. So back in the code here, we first call the getModuleHandle API to get a handle to the executable base address in memory. This handle is actually a pointer to the first byte of the executable in memory. The next thing we need to do is to get the actual size of the executable headers in bytes. The header size is actually stored inside the executable itself, and it can be found under the optional header in the size of headers member. This member stores the header size in hex. Typically, the header size of most executables is either hex 400 or hex 1000, so you can simply hard code this value here. But this is lame. We didn't really learn anything here. I could simply just tell you to hard code this value here and call it a day. But we are pro hackers here. We don't just hard code values or copy and paste code like script kiddies do. We have to understand pretty much everything that's happening behind the scenes. So instead of hard coding the header size here, we will extract it dynamically from the executable memory at runtime using this code. Wait, don't close the video. Just hear me out, okay? I know this code might look scary or vague to you if you're a beginner, but if you want to really learn how actual malware is built, you need to understand this. So here's the thing. In the next 4 to 5 minutes or so, I'm going to make this code here a walk in a park for you. And if you understood the whole thing, you will have to subscribe. Do we have a deal? We have a deal. Alright, cool. Now, before we understand what this code is doing, we need to ask ourselves one question, which is, what are we trying to achieve here with this code? We need to obtain or extract the value of the size of headers member from the memory of our process at runtime. And in order to do that, we need to understand the structure or the layout of the portable executable headers. We first have the DOS header. This header has a total of 19 members. The member that matters to us is the ELF and new member. This member stores the address or the offset of the NT headers. The NT headers consist of two main headers, the file header and the optional header. From CFF Explorer, we know that the size of headers member is located inside the optional header. So now, once we obtain the address of the NT headers from the ELF and new member, we can simply access the optional header and obtain the value of the size of headers member like this. So back in the code, we first create an instance of the image DOS header struct. This struct contains all the members of the DOS header, and it's already defined inside the Windows header. So we don't need to redefine it in our code. We just include the Windows header in our code and then create an instance of the struct like this. The next thing we need to do is to populate the struct. We already created an instance of the struct, but it's still empty. So here we use the reprocess memory API to read the executable DOS header. We know that the DOS header starts at the MZ magic bytes, or the very beginning of the portable executable. That means we need a pointer to the base address of the executable in memory, and we already obtained that using the getModuleHandle API. So here, we first provide the handle to our process using the getCurrentProcess API. Then we specify the source or the base address of the chunk of memory that we want to read, which is the base address of the executable, and it's typecasted to LPC void so that the reprocess memory API can work with it. After that, we provide the address of the struct that we want to populate, which is the image DOS header struct. Next parameter is how much memory we want to read, and we set that to the size of the whole struct. And then the number of bytes read. We set that to null as it's not that important to us. If you're still confused about how the reprocess memory API works, here's a visual representation. I explained before in our first video of the series that in order to calculate the size of the whole struct, you have to add up the size of each member. For example, let's calculate the size of the image DOS header struct. Here we have 16 words. The size of a single word is 2 bytes. So 16 times 2 equals 32. Then you have an array of 4 words plus an array of 10 words, which equals to a total of 14 words. That results to 28 bytes. So 32 bytes plus 28 equals 60, plus a 4 byte long equals 64 bytes, the size of the whole struct. We can confirm that by printing the size of the struct like this. So now, the reprocess memory API will go to the base address of the executable in memory and read 64 bytes from there, and then it will populate each member individually. For example, let's assume that this is the chunk of memory that we want to read. The reprocess memory API will first check the size of the first member in the struct, which is a word, or 2 bytes. So it reads 2 bytes starting from the address that we specified, and store them inside this member. Then it checks the size of the next member in the struct, which is also a word. So it reads the next 2 bytes and stores them inside the second member. And it keeps doing that until all the members of the struct are populated with the 64 bytes of the DOS header. So now we can simply read the value stored inside any member of the struct like this. Back in the code, after we populate the image DOS header struct, we read the value of the ELF and new member, because this value is the offset or the address at which the NT headers start. And inside the NT headers is the optional header that contains the size of headers member that we want to obtain. So here we add the offset of the NT headers to the base address of the executable in memory. This is called the virtual address of the NT headers, or the address of the NT headers in memory. And if you're wondering why we add it to the base address of the executable here, it's because this is an offset from the base address of the executable. The raw address, or the address on disk at which the executable starts, is 0. That means in order to obtain the address of the NT headers on disk, we add up the address stored inside the ELF and new member and the base address of the executable on disk, which is 0. But when this executable is loaded in memory, its base address is no longer 0, and we don't know exactly where it's loaded in memory. So we use the get module handle API to obtain its base address in memory. And once we have it, we add it to the offset of the NT headers the same way we did on disk. Also here, we typecast the handle returned by the get module handle API to LP byte to convert it to a byte pointer so that we can do pointer arithmetic operations on a byte level. Now, since we have the virtual address of the NT headers, we create an instance of the image NT header 64 struct. You can see the definition of any struct in Visual Studio by holding Control and clicking on it. We can see here, similar to CFF Explorer, the signature member and 2 subheaders, the file header and the optional header. So next, we use the reprocess memory again to populate the NT headers, the same way we did with the DOS header. And once the NT headers are populated, we simply read the value of the size of headers member under the optional header, like this. And that's it. It's as easy as that. I think you should subscribe now. Anyway, that was the hard part. The easy part now is to erase these headers. What I mean by erase is to set all bytes in the headers to 0. By default, the protection of the portable executable headers is read-only. So before we zero out this region of memory, we need to modify this protection to read and write, or we will get an access violation error. So here, we use the virtual protect API. We first specify the base address of the memory region that we want to modify its protection, which in our case here is the base address of the executable. The next parameter is the size of this memory region. Since we want to erase all headers, we set it to the size of headers. Then the protection that we want to apply on this memory region, which is read and write. And finally, we store the old memory protection in this variable to restore it later after we erase the headers. Once the protection of this memory region is modified, we use the zero memory API and we give it the base address of the executable and how many bytes we want to set to 0. Since we want to erase all the executable headers, we set it to the size of headers. If you don't want to use the zero memory API, you can use a for loop like this that sets all the executable headers to 0 starting from the base address like this. This is equivalent to this. They both work. Finally, after we erase all the headers, we restore the old protection using virtual protect like this. Now, before we compile, let's add a get char function before and after the headers are erased to halt the execution flow so I can show you the process memory before and after the headers are erased. Now, open Process Hacker or any similar tool. I have Process Informer running here, which is the successor to Process Hacker. Now, run the compiled executable, and in Process Informer, open the process properties, and in the memory tab, you'll find the base address of the executable. We can see here the headers protection is read-only, and the headers are still untouched. But when we resume execution, we can see here the protection changed to read and write, and all the headers are set to 0. You can now employ this anti-dump mechanism with anti-debugging techniques. For example, we can use something like isDebugger present to check if our process is being debugged, and if so, we call our self-destruct function to erase the process headers, preventing it from being dumped from memory. For sure, a simple anti-debugging mechanism like isDebugger present can be bypassed easily, but imagine employing this anti-dump mechanism with every anti-debugging and anti-VM mechanisms in the book, which is what we're going to do in the upcoming videos, so subscribing is mandatory right now. Anyways, now you know a little bit about the portable executable headers. We barely scratched the surface here. In the upcoming videos, we will dive deeper into the structure of the portable executable, and we'll learn stuff like building and detecting packers, multiple stage loaders, Win APIs, custom implementations, and a lot more. But we have to cover most of the basics first, so don't forget to sub. Join as a member if you can. The tiniest support really matters a lot to me.